Hello class, today we'll be talking about series, and more specifically we'll be referring to arithmetic and geometric series. Now, the big difference between series and sequences that we have been talking about is that sequences, let's say I'll give you a sequence, 1, 2, 3, 4, yada yada yada. This talks about a list of terms that are just a list and separated using commas. If we're talking about a series, we'd be talking about this list and finding the sum of all these terms. So below, here, in this area, this is a way to actually find the sum of a finite arithmetic series. I'm going to go through right now, talk about what each part of this is. So the first part is, here, n focuses on which term you're speaking about. So if you're talking about the first term, you'd be talking about the count n, 1, for both these. And I suppose I should only be looking at our series now. So, talking about count 1 for the first term, count 2 for the second term, and count 3 for the third term, so on and so forth. So n is your count. T1, now that's referring to your first term. So in this case, let's say I was trying to find the sum from 1 to 50. So let's type that out. The sum, find the sum from 1 to 50 in this list. What you would look for is having the final term here, Tn, be 50, since 50 is the end of your list. And all of this is divided by 2. If you want to know more about this specific formula, feel free to check out my other video on the proof of this formula for a finite arithmetic series. So let's plug this in really quick and see what we end up getting. We're going to get the sum, Sn, for the n is the number of terms in your series, so it's going to be 50 terms, divided by 2, with your first term in parentheses 1 plus 50. So in this case, you're going to get 25 multiplied by 51. You get an answer of 1275. No, I don't like it. Yeah, I'll be fine. 1275. Now, I may write it differently in the future. I'm going to show a slight variation to this written formula, and that will be the following. To say that Sn again is equal to, now I would write it like n over 2, pulling that out on its own, and multiplying it by t1, saying this is that, again, a function, and t of n for the count. So that's another way of writing it, and those are the two different formulas for this. So let's try to apply this to a problem. Alrighty, in this example we're supposed to find the sum of the first 30 terms of the specific 12 plus 18 plus 24 plus 30 plus ... series. So I urge you to pause the video now and make an attempt at finding the sum applying the formula we had just used. So let's get started. I'm going to first start off with writing out the formula, saying that the sum of our series is going to be equal to the count of the number of terms in our series divided by 2, and our first term here, which is 12, plus the, oh no, it doesn't seem like we have our final term. What are we ever to do? Well, this is where our relationship of sequences and series comes into play. If you actually looked at it and noticed that the difference between each one of these terms is 6, you can say the common difference is 6 here, and if we were looking for the 25th term, the 30th term, my apologies. Let me erase this. 30th term. Then in this case, we can simply say that the first term is 12 plus the common difference multiplied by the number of terms, which is 30 minus 1. And this is going to give us our 30th term. So this should be 29 times 6, which is 174, and 174 plus 12 is 186. So 174, 12, and this is going to be equal to 186. So that is going to be our 30th term, and we plug that in right here. So it's a little bit more work, but definitely less work than doing all those terms out. So I forgot to throw in my 30th term here, so let's plug that one in. 30 divided by 2, and 12 plus 86, 198. So you have 198 times 15, and you get 2,970. And that's the sum. So we have more types of series than just arithmetic. We also have geometric. And geometric here is shown with this formula. S sub n is equal to the first term multiplied by 1 minus r raised to how many terms you have in your series. Then all this is divided by 1 minus r. And here, r is equal to the common ratio and it can't equal 1. Actually, let me write r can't equal 1 to be more specific. In this case, if r was equal to 1, then you'd be dividing by 0. Can't have that. So let's just put this to the test and use it in this formula below. If you notice, the common ratio here is 3 is equal to r. And if we were to plug this in for s sub n to find the sum of the series, we have our first term 2, 1 minus 3 raised to the n. Well, how many terms do we have? We have 1, 2, 3, 4, and I think this is just the fifth. Yeah, we have only 5 terms here. So we have 3 raised to the 5th over 1 minus 3. Do this out, we're going to get 2. 3 in this case is going to be raised to the 5th, which comes out to 243. 1 minus that number, you're going to get negative 242 over negative 2, which comes out the negatives will cancel out along with the 2's. You're left with 242 as your sum. So this is a more simplistic way of doing the geometric series. We're actually going to do one more with slightly more difficult numbers and common ratio. Alright, for this example, we wanted to find the sum of the first 10 terms of this geometric series. So again, we're going to rely on our formula here, and I urge you to go see the proof in my other video if you'd like to see this. It is a more complex proof, but I think it's actually very interesting the way it is proven in terms of cancellations and how we had to do a little bit of, not funky math, but math to reason it out in a usable fashion. So I hope you enjoyed that one. So let's just test this out here. So we have our sum of our series. T1 as our first term, and actually I want to keep it in my notation. T of 1 multiplied by 1 minus r raised to the number of terms in the series, and over 1 minus r, the common ratio. So let's plug these in. The common ratio here, if you notice, will be, that's, well, 3, but, oh, this is very similar to the last one, but this is negative 3 in this case. Doesn't always have to be a positive ratio. So in this case we have 2, 1 minus 3, and that's raised to the 10 over 1 minus 3 again. And if we solve this out, negative 3 raised to the 10th is going to be 2 multiplied by 1 minus 59,049. So 59,049 over, in this case, 4. This cancels out to 1/2. Pull that to the side, and this is going to be simply 59,000, because those would become positive, 0.50. Divide that by 2. 59.50 is going to be 29,525. So looking back on this, I did notice that there is an error right here, and I'll highlight it with the point tool, right from this point here to this point. So it actually doesn't come out to be, draw this, it doesn't come out to be negative 3 to the 10th equals negative 59,049. Should be positive, because if you notice we have an even number we're raising it to, so this should cancel out the negative. So what happened here in my calculator, I accidentally wrote this, which gave me a negative number. Be very careful. I always keep saying, notice your parentheses, and here, made my own mistake. So in this case, make sure you have your own parentheses, and this should be a positive here, which means that in this case we should have a negative, and this should be 48. So I'm going to erase this. It should become 48. And we should get, let me erase the final answer, so it's 1/2 of 59,048. That's 1/2 of that. You get 29,524. I can't forget the negative. And there we go. And that's what you have as an answer for this finite geometric series. Like I said before, please make sure to look at other videos for proofs on these infinite sums of geometric and arithmetic series. And I also want to note that in your chapter you should note that there are other type of series that can exist that aren't geometric, or nor are they geometric. So those don't have formulas, but they do have recursive formulas, ways of writing them, so we can calculate out some nth term using a computer simulation. So hope you enjoyed the video. Have a great day.